All right, today we are diving into a really cool piece of tech. We're talking about something that can create electricity at absolutely blistering temperatures and with remarkable efficiency. This is a true powerhouse that could totally change how we think about fuel. So let me just start by posing a question. What if you could take a common fuel, something like natural gas, or even gas from coal, and turn it directly into power? Completely sidestepping all the usual inefficiencies of a traditional combustion engine. Well, that right there, that's the core promise of the technology we're going to break down today. And that technology is the Molten Carbonate Fuel Cell, or MCFC for short. It's an absolute powerhouse. And really, the whole secret to its power lies in one defining, and let's be honest, very extreme characteristic. And that characteristic is heat. A lot of it. MCFCs operate at an average temperature of 650 degrees Celsius. That is hot enough to melt aluminum. But here's the key. This intense heat isn't just a byproduct. It is absolutely fundamental to how the entire system works. And it's what gives it some pretty incredible advantages. Think about this. That extreme heat has a major economic impact. At 650 degrees, the chemical reactions happen so fast on their own that they don't need expensive precious metals like platinum to get them going. Right away, this gives MCFCs a huge cost advantage over many other types of fuel cells that rely on those pricey catalysts. So when you kind of zoom out and look at the big picture, the pros are really significant. You get very high efficiency, and you get the flexibility to use different kinds of fuels. But, and it's a big but, that intense heat also creates some major challenges. It causes severe corrosion, and just managing the molten salt electrolyte inside the cell is this constant critical battle for the engineers. Okay, so how does this hot, molten salt-filled box actually generate an electric current? Let's pop the hood and take a look at the chemical engine that drives this thing. And don't worry, we're gonna keep it simple. It all really boils down to a three-step dance. First, at one end, the anode, hydrogen fuel reacts and bam, it releases electrons. Now those electrons are forced to travel through an external circuit, and that controlled flow of electrons is our electricity. Then they finally arrive at the other end, the cathode, where they react with oxygen and some carbon dioxide to complete the process. And this is where the design gets really elegant. You see, the carbon dioxide that gets produced at the anode isn't just thrown away as waste. No, it's actually an essential ingredient. The whole system is designed to capture that CO2 and pipe it right back over to the cathode where it's needed to keep the reaction going. It's this beautiful, self-sustaining loop that's totally fundamental to how the cell operates. So we've covered the process. Now, let's break down the physical hardware that makes it all happen. What are the key components inside one of these MCFCs? Okay, first up is the anode. That's the negative electrode. This is basically the front door where the fuel comes in. Its whole job is to kick off that initial reaction that strips the electrons from the hydrogen. It's a porous metal structure, usually a nickel alloy, and it's designed that way to maximize all the surface area for the fuel to react. And on the other side, you've got the cathode, the positive electrode. This is where those electrons end their journey. It's made from a material called lithiated nickel oxide, which is specially engineered to be tough enough to survive the incredibly corrosive, high-temperature world inside the fuel cell. Now, connecting the two is probably the most unique part of the whole setup, the electrolyte matrix. The best way to picture it is as a ceramic sponge. This sponge, made of lithium aluminite, is just soaked with that molten carbonate salts. And its job is brilliant. It acts like a very specific traffic cop. It lets charged carbonate ions move from the cathode back to the anode, which completes the internal circuit. But, and this is the whole trick, it physically blocks the electrons. It forces them to take the long way around through our external wire, which is exactly how we get useful electricity out of it. Now, as you can imagine, operating at 650 degrees Celsius is not easy. It creates a massive engineering puzzle. So let's look at the specific challenges that scientists and engineers are wrestling with right now to make these fuel cells last longer and perform even better. This quote from the research really cuts to the heart of the single biggest problem. The cathode, that tough nickel oxide part we just talked about, literally and slowly dissolves into the molten electrolyte over time. So finding a way to stop this, or at least dramatically slow it down, is the #1 priority for extending the life of these cells. And of course, that's not the only headache.
the anode material can slowly deform or creep under all that heat and pressure. The metal plates that connect all the individual cells together in a stack get eaten away by that corrosive salt. And all the while, you have to carefully manage the electrolyte itself to make sure it doesn't just evaporate or wander away from where it needs to be. It's a seriously tough environment in there. But, for every challenge, there's an innovation. And the next big leap forward for MCFCs is all about making the system smarter and more integrated, which helps tackle some of these problems while boosting efficiency even further. And the big idea here is something called internal reforming. So instead of having a big, separate piece of equipment to convert a fuel like natural gas into hydrogen before it even enters the fuel cell, internal reforming does that job right inside the fuel cell stack itself. Now, there are two main ways folks are doing this. With indirect reforming, or IIR, you have a special plate with the catalyst placed right next to the anode. But with direct reforming, or DIR, you go a step further and actually put the catalyst particles right inside the anode compartment itself. The end goal is the same, but the engineering approach is just a little different. And let me tell you, this is a total game changer. Getting rid of that bulky external reformer makes the whole power plant simpler, cheaper, and more reliable. And what's even better, that chemical reaction for reforming needs heat. And hey, the fuel cell is already running at 650 degrees. It uses its own waste heat to power the reaction, which is a brilliant way to boost the overall system efficiency even higher. So that really brings us to our final question. With all these ongoing improvements in material science and clever engineering tricks like internal reforming, these high-temperature powerhouses are just getting more durable and more efficient. So could they become a key piece of the puzzle for stationary power? Providing clean and flexible energy for our future grid? It is definitely something to think about.